So for this question, we're given two equations on the same graph. This one in red that's a straight line is labeled as g of x, and this parabola, which is a curve, is labeled as f of x. And we have a few questions related to this graph. And the first one, part A, is f composed with g of 1. And we're going to use the graph to answer this question. So to find f composed with g, we have to know what this operation of composition means. This operation is exclusive to functions. We haven't seen it before related to numbers. And this operation means that we want to substitute one function inside of another function. Our outside function is the function before the composition symbol, and the inside function is the one after the composition symbol. So I've just rewritten this in an equivalent form with that idea of substituting one function inside of another function. So this is the same thing as f of g of 1. And now that it's written in this format, we can recognize some order to the symbols. Inside the parentheses, we see some symbols that have meaning to us. This is our function notation. We want to evaluate the function g at the value of 1. So we know that x is equal to 1, and we want to find the y. So using the function g, we're going to look for an x value of 1. So all along this vertical line are all ordered pairs with an x of 1. And we want to specifically focus in on this ordered pair because it's on the graph of g, and that y value is 2. So we know that g of 1 is 2. So we can replace that g of 1 with 2. So now we have function notation once again, and we want to evaluate the function f at a value of 2. We know that x is 2, and we're looking for y. So once again, we go to our graph looking for an x value of 2. All of these ordered pairs along this vertical line have an x value of 2, and we're specifically going to focus on this one here, which is on the graph of f, and that has a y value of 0. So f of 2 is 0. So we were able to figure out that f composed with g of 1 is 0. I have another one for us to try. So this will be part B, where we're looking for g composed with f of 1. Let me erase the markings that I had before so we don't get confused by all this notation. And once again, we're using that operation of composition. So we're going to rewrite our function as g of f of 1. On the inside, we recognize the symbols f of 1, and we know that x is equal to 1, and we're looking for y. So on our graph, along this vertical line, has x values of 1, and we're going to focus in on this one here, which has a y value of -1. We focused on that because that's where the graph crosses f. Excuse me, that's where the line crosses f. And so that value, that y value, is -1. So we know that f of 1 is -1. So we can replace f of 1 with -1, And now we're looking for g of -1. If I draw a vertical line where x is equal to -1, you can see this spot here is where it crosses the graph of g at a y value of -2. So g of -1 is -2. So we found that g composed with f of 1 equals 2. So we have several more parts, and the next one, part C, we are finding g composed with g. And we recall that this operation of composition is substituting one function inside of another function. So we'll rewrite this as g of 0. Let me erase my markings. Okay, so I'm going to try not to mark so much this time. We're looking for g of 0, which is right here. G of 0 is 0. And then we simplify again. G of 0 is 0 again. Let's zoom out so we can see all the parts. We're going to do part D, which is f composed with f of 3. We'll start by rewriting this as f of 3. So I'm going to start by looking for f of 3. So I start with an x of 3. I'm looking for where that is on the graph of f, and the y value there is -1. So f of 3 is -1. And I need to find f of -1. Here's an x of -1. I'm going to find where that x of -1 is on the graph of f, and that is at -9. So f composed with f of 3 is -9. Take a look at part E. For part E, we're going to do f composed with g composed with f of 2. So we have several compositions here, and going from left to right, we'll start on the most outside and then work our way inside. So this will be f of g of f of 2. So first we want to find f of 2. So here's where x is equal to 2, and on the graph of f, that y value is 0. I can replace f of 2 with 0. Then I want to find g of 0. An x value of 0 is here. On the graph of g, that y value is 0, so g of 0 is 0. So I replace g of 0 with 0. And then I want to find f of 0, and that is right here on the graph, and that has a y value of -4. So we found f composed with g composed with f of 2 to be -4. And we finally have one more to go. That's g composed with f. This is part F. G composed with f composed with g of 0. And on this one, we'll rewrite it as g of f of g of 0. And we've already seen a few times that, let me highlight it, that g of 0 is 0. So we're going to replace g of 0 with 0. And we want to find f of 0, and we've seen f of 0 right here is -4, so we can replace f of 0 with -4. And then we need to find g of -4. Here's an x of -4, and we have a y value of -8. So g of -4 is -8. So we found g composed with f composed with g of 0 to be -8. On this question, it says, is the function one-to-one? Use the horizontal line test. Okay, so I've added in this definition of what a one-to-one function is. A function f is one-to-one if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So this is saying that if we have x values that are different, then our y values will be different. And so this is a test that we use to basically show if the y's are unique. Now the horizontal line test is how we decide whether that whether that graph is a one-to-one function. And the reason why we use a horizontal line is because if we think about the graph of a horizontal line, and we think about the ordered pairs that are on that horizontal line, all of the ordered pairs will have the y being the same. And so we want the y's to be different. The horizontal line has all the y's being the same. So it's a good comparison to our graph. The horizontal line is the opposite of what we're looking for. So on this graph, we're going to draw horizontal lines, and we're going to pay attention to the intersection points. And since these horizontal lines are intersecting the graph in only one point, we know that there's only one y value. Those y values are not repeating. All the y values are different. Now, it may be a little bit confusing if we focus in on this part of the graph, because it looks like the graph turns into, it looks like the graph turns into a horizontal line as we get closer and closer here, but this portion of the graph never turns into a horizontal line. There's always going to be a little bit of a gap in between this line and the x-axis. Even though we can't see it, if we were able to zoom into this, there would always be a little separation between the line and our graph. And so what's happening to the graph is it gets closer and closer. It never reaches it. So when we do the horizontal line test here, we're only crossing in one place. So in this particular example, this function is a one-to-one function. I've zoomed this way too big. Sorry about that, guys. So this function is one-to-one. For this one, we want to know, is the function with the graph one-to-one? So we're given this picture, and we want to know whether it represents a one-to-one function. So I've copied here the definition of one-to-one. A function f is one-to-one If for any values a not equal to b in the domain of f of a is not equal to f of b. So if we simplify the meaning of this definition, this is saying x is not equal to a is not equal to b. That's saying that the x's are different. And then over here we have f of a not equal to f of b. This is saying that the y's are different. And on this function, we can come up with what we call a counterexample to this definition. So if we take a look, say for instance right here, this is a situation when these two y values are the same at these 2 points. They have a y value of 3. However, the x's are different. So here it says if the x's are different, then we have the y's different. Here we have the y's being the same and the x's are different. So if the x's are different, we should have all the y's being different, and that is 1 to 1. So in this example, we don't have a 1-to-1 function because it's not following the definition of the x's being different than the y's being different. Here we have x's that are different and the y's being the same. Now, we do have a strategy that we typically use to decide whether the graph represents a 1-to-1 function. And what we use is something called the horizontal line test. So when you have a graph and you're trying to decide if it's a 1-to-1 function, you're going to draw horizontal lines all over the graph. And what you want to pay attention to are the intersection points of your horizontal line. So we'll notice that this has one intersection point, but all of these ones down here have 2 intersection points. So when we get 2 or more intersection points, this is an indication that the function is not 1-to-1. And because you have a horizontal line, horizontal lines have all the same y values. So what you're getting with a horizontal line is y values that are the same. And so when you get 2 intersection points, you're getting 2 points that have the same y value. So y's that are the same, x's that are different, and that is a violation of the definition of 1-to-1. So this particular function is not 1-to-1. Now, if you draw horizontal lines and you only get one intersection point or no intersection points all over the graph, then you can say that it is a 1-to-1 function. The function f of x is equal to 1/6 x minus 2 is 1-to-1. We want to find the inverse of f and state the domain and range of f. We also want to state the domain and range of f inverse. So we know that this function is 1-to-1, and that tells us that the inverse will also be a function. So let's find the inverse, and we're going to use a 3-step process for finding the inverse. We have f of x equals 1/6 x minus 2. And our first step is we're going to change that f of x to y. Now this step just makes the equation a little bit easier to work with. And the next step is we're going to switch the x and the y. This is what's going to help us find the inverse. So our equation would be x equals 1/6 y minus 2. Inverse functions switch the x and y, so we're going to switch the x and the y to find the inverse. And the final step, we're going to solve for y. So I'm going to add 2 to both sides. That gives x plus 2 equals 1/6y. And then I want to get rid of that 1/6, so I'm going to multiply both sides by the reciprocal, which is 6. And this gives y equals 6x plus 12 if I use the distributive property on the left, and on the right, the 6 times 1/6 becomes 1. So now we have our inverse function. F inverse of x is equal to 6x plus 12. And we found the inverse. We also want to state the domain and range of each of these functions. So let's write them down over here. We have f of x being 1/6 x minus 2, and f inverse of x is 6x plus 12. So we're trying to find the domain and range of each of these functions. And when I take a look at them, I have a strategy for finding the domain. This is a linear function because we have x to the first power. A linear function is a type of polynomial. And polynomial functions have no restrictions on their domain. So I know that the domain of f is all real numbers, -infinity to infinity. When I look at f inverse, I also see a linear function, which is a type of polynomial. So it also has a domain of all real numbers, -infinity to infinity. And as we said earlier, inverses switch the x and y values. So the x's and the y's, the domain and range, also get switched. So if I'm looking for the range, if I'm looking for the range of f, I'm going to use the domain of the inverse because, remember, those x's and y's get switched. So the range of f is -infinity to infinity. And then if I'm looking for the range of f inverse, I'm going to use the domain of f. That's going to be -infinity to infinity. So I've found the inverse, and I've also found the domain and range of each one of these functions. Write an equation for the inverse function and then state the domain and range of f and f inverse. In this question, we have the function f of x equals x cubed plus 4. The first thing I want to do is find the inverse function, which we call f inverse. So to find that inverse function, I'm going to change f of x to y. And then I'll switch the x and the y. And I'm switching the x and the y because that is what inverse functions mean. The x and the y are switched in these type of equations. So that's basically by definition because we're looking for an inverse function. And then I'm going to solve for y in this new equation. So I want to isolate the y. So to isolate the y, I'll subtract 4 on both sides. And I need to get rid of that cube, and the opposite of cubing is cube rooting. So I'm going to cube root the left and cube root the right. The cube root and the cube cancel each other out, giving me y. And then on the left, I have my inverse function, cube root of x minus 4. So we can label that as f inverse. F inverse is the cube root of x minus 4. The next thing that we want to do is find the domain and range of f and f inverse. Now we have some strategies for finding the domain of different types of functions. So I'm going to find the domain of each of these f and f inverse first. So if I look at f of x, that is x cubed plus 4. This type of function is called a polynomial function. And with polynomial functions, there are no restrictions on the domain, meaning that no matter what real number we substitute in, we are going to have a defined y value. And so because of that, we can say that the domain of f is all real numbers, negative infinity to infinity. We'll do the same thing for f inverse. We just found that f inverse is the cube root of x minus 4. As I look at this function, I would categorize this as a root function. We call it a root function because of the radical. Now with root functions, you want to pay attention to the index. This has an index of 3. And the reason why you want to pay attention to the index is because root functions with an even index have restrictions on the domain, but root functions with an odd index have no restrictions. So we have an index that is odd, so there will be no restrictions on the domain of this function. The domain of f inverse is also all real numbers are negative infinity to infinity. Now we also want to find the range of f and f inverse. Now we don't have as many strategies for finding the range like we did the domain. But if you'll remember, what we did earlier is we switched the x and the y. So what we know about inverses is that the x and the y switch. Domain are the x's, range are the y's. So if we switch the x and the y, the domain and range also get switched. So what that means is that I can use the domain of f inverse as the range of f. And I can use the domain of f as the range of f inverse. So we now know that the range of f is all real numbers, negative infinity to infinity, and the range of f inverse is all real numbers, negative infinity to infinity. Thank you for checking out my videos. Have a great day.